Start with the next session. The first speaker is Steve Scott from Google.
All right, thanks a lot. So I want to start by, I guess it's traditional to start by thanking the organizers. I'd like to start by congratulating the organizers because I think this has been a really good meeting so far, and there's very few meetings that I've been to where I've been really excited about the talks that are coming up to the extent that I am with this one. So I think that you've done a really good job lining up speakers, and I'm just going to try to not disappoint with my own talk here. My talk is about consensus Monte Carlo, which is a topic that I've been describing, I've been on the talk circuit with this talk for several years now. Some of you have already heard part of this. There is some new stuff at the end. The outline of the talk, I'm going to start with some introductory remarks. I'll go over kind of the basics of consensus Monte Carlo, show you some examples of where things work pretty well. For those of you who have seen me speak on this topic before, this will be familiar. I do want to spend a little bit more time talking, focusing in this talk on some of the alternatives to the method that I favor for doing the divide and conquer recombination that people have come up with. This isn't necessarily the most cutting edge stuff, but they are techniques that people have. When I have conversations with people about the right way to do Bayes and big data, they say, have you seen this paper? This guy gave this talk. Have you talked about particles, things like that. And what I wanted to do is to kind of give some examples at using these alternative methods and show where they struggle. And then I'll just conclude. So really most of this talk has no mathematics to it at all. It's all just kind of computing and examples. So what am I going to tell you? So if you go to sleep and wake up at the end of the talk, this is what you would have missed. I think that there's the phrase big data didn't show up in the title of this meeting. Thank God. I sort of am happy that maybe it's sort of past its point of peak frenzy, the phrase big data. It is still a phrase that I hear a lot in my life. And when I think about scaling statistical methods, the people that I spend most of my time with aren't necessarily statisticians, but they're Google engineers. And Google engineers don't necessarily think about scaling things the same way that statisticians think about scaling things, right? To a Google engineer, when you say something is scalable, it means that you can run it on multiple machines. And if you tell them that you have a big data problem, and you have 100,000 observations or something like that, and that's a big data problem, they sort of look at you with a crooked head. If you've ever confused a dog, and you've seen that sort of confused kind of look that they give you, you get one of those from the engineer, and they say, well, your problem fits in memory. That's not a big data problem. And so I'm interested in the types of big data, scalable types of problems that require multiple, the cloud, right? Cluster computing, that kind of things that require multiple machines. When you live in that world, you have basically an infinite supply of all of what we typically think of as computing resources. So you have infinite CPU, infinite processing power, you have infinite memory. So Havard, his problem when he was running out of memory. Well, on the cloud you have infinite memory, and you have infinite disk, right? And when you go and buy a computer, those are the things that you try to sort of scale up. But of course, there's no free lunch, and there's always going to be a bottleneck somewhere. And the bottleneck is that in the multi-machine environment, communicating between different machines is very expensive. And in past versions of the talk, I've gone on a little 10-minute diatribe about just how expensive it is. But it's expensive enough that communications can't really be in the interior loop of your MCMC algorithm in the way that they can if you're coding on GPUs or multiple threads on the same CPU. And so if communication is a problem, then the obvious solution is to not communicate. And that's what consensus Monte Carlo is about. Consensus Monte Carlo is about the phrase divide and conquer has come up here a few times. It's that type of algorithm where you take your data and you chop it up into multiple pieces that people at Google like to call shards, like when you break a glass and it partitions itself into a bunch of shards. And then you do a separate MCMC or Hamiltonian or whatever your favorite Monte Carlo method is on each of the shards, and then you put them back together. And then the question is how, right? And that's the primary focus of this talk is what are the right ways to recombine these different analyses in the consensus or divide and recombine method. I'm a big fan of just averaging the draws, right? So you've got a draw 1 and a draw 2 and a draw 3, and you've got a draw 1 and a draw 2 and a draw 3, and I'll average your draw 1s and average your draw 2s. That's obviously got some, I'm going to show you some examples where that really works great, right? But there's obvious benefits, right? In hard problems, that's not going to work so well. And so people have been working to try and find alternative methods to do when averaging doesn't work well. And so what I want to do is compare, in this talk, in at least the second half of it, compare the averaging method of doing consensus Monte Carlo with some of the alternative methods that have been proposed. And what we're going to find is that the alternative methods, they work really well in 5 dimensions, right? And they don't work really well in 10, right? So the recursive dimensionality starts to fall apart and bite really hard at very, very, very low dimensions. And that's a problem because if you think about, why we live in a big data world, well, you live in a big data world because you're going to fit a complex model, right? And complex models tend to be models that have lots of parameters, and so if your solution falls apart in 5 dimensions, then or after 5 dimensions, then that's sort of a bad deal. All right. Okay, so I guess I mentioned this just before. This is not a meeting about big data, but it's definitely, big data is definitely a phrase that hasn't disappeared just yet. And I think that I've already mentioned kind of the difference between how statisticians think about big data versus the data science and engineering world. To a statistician, you have a big data problem if your MCMC is too slow, right? I have so much data, I can't just do my Metropolis Hastings or something like that. And so I think there's a lot of emphasis from a lot of talks about at this meeting about how to make MCMC go faster. But a lot of those talks are focused on the MCMC that you want to run on your laptop or your workstation, right? And things like subsampling and kind of there hasn't been a lot of parallel like multi-core talks, but I think some are coming later. And the continuous time stuff, things like that. I want to emphasize that those things and the stuff that I'm interested in are in no way in conflict, right? And I think actually those things are more important because there's more laptop-sized problems in the world than there are cloud-sized problems in the world, right? So I'll just sort of leave it there. And the last thing I have on this slide is sort of the public definition of big data, which I think is just data. When you hear the newspaper articles and things like that talk about big data, I think people they use the word big in the same way that they use big oil and big banks and the big bad wolf. Data is a new thing that they didn't have to think before, and it's mysterious and scary, and they don't know what to do about it. So the term is just sort of ill-defined. Okay, so if we want to focus on the thing in the middle, with machine learning, engineering, that type of big data, you solve big data with big iron, right? And so I'm not interested necessarily in algorithms that are going to run on the laptop. What I really care about is algorithms that are going to run in data centers, right? Data centers look like this. That's your computer now, right? It's some building in Finland with big fjords that you can use to cool all the heat and stuff that all these machines generate. It's not hard to run a job on 1,000 or 10,000 or multiple tens of thousands of machines in this world, right? And I mean, for Google, it's been that way for 10, 15, 18 years now, right? For everybody else, for the last, I don't know, maybe 10 years or so, Amazon launched their EC2 computing service. And so for the last 10 years, you've been able to rent space on clouds like this. And you think, well, okay, yeah, but I'm just sort of a poor academic. I can't afford to, do this rental. But the pricing for these machines tends to be something like a penny an hour, right? For the cheapest machine that you can buy, it's something like a penny an hour. And if you think about what you might pay an undergraduate research assistant to work on your problem, you're looking at, maybe $15 or $20 an hour. I don't know what undergrads get paid these days, but for $15 an hour, you can have 1,000 computers work on your problem for an hour, right? And that's going to solve a lot of problems. Right. So what I'm talking about, the thing that I have in my sights here with this methodology is not just something that people only at Google and Facebook and Microsoft can do. It's something that anyone can do as long as you kind of spend a weekend setting up your compute rig on one of these cloud systems. Okay. So yeah, this is a screenshot from Amazon EC2, and here we have the cheapest machine, if you want a Linux machine, is slightly under a penny an hour, and it's probably gotten cheaper because more companies have gotten into the cloud space, and competition will make the prices go down. And with each one of these machines, remember, not only do you get the CPU that comes along with it, but you get, I don't know, some number of gigs of memory and some number of terabytes of, you get whatever a CPU would come with memory and disk as well. There's the Google stuff. Okay. So given that we have access to this massive, massive computing power that just dwarfs anything that we could go, get from the local electronics shop, the question is, how do we use it? And so that's consensus Monte Carlo, right? I'm skipping some stuff that I normally put into this talk here, where I motivate exactly how bad things would be if we were to do naive algorithms in the cloud. But just sort of trust me, communication between machines in this world is something that takes a long time. So the communication-free algorithm version of consensus Monte Carlo goes like this. So I've got data that I'm going to chop into capital S pieces, y1 up to ys, right? And then conditional on each one of these pieces, I'm going to put y1 on machine 1 and y2 on machine 2. I'm going to run a separate Monte Carlo on each of my shard level posteriors. Some people call these sub-posterior distributions in the literature, to get a set of posterior draws from p of theta given y sub s. So each machine is going to run a full Bayesian analysis as if the shard of data that it saw was the only data in the world, and it doesn't know about the other shards. All right. And then once I have those sub-posterior distributions, I'm going to combine them, put them back together to form what I call a consensus posterior distribution. So if you are thinking about the world in terms of divide and recombine or divide and conquer, this is the divide step and this is the recombine step, right? And if we think about, if we sort of think logically, mathematically about this, there's got to be a way to make this work, right? Because when we write down the posterior distribution given the full data, p of theta given y, for lots and lots and lots of problems, you can write this down as the prior times the likelihood, and the likelihood will factor across these different shards. This, might not, spatial models, okay, time series, all right. You can think of examples where you can't write things down like this, but for lots of problems, you can find something conditionally independent somewhere where you can write down the posterior distribution this way, right? And so mathematically, the problem factors, right? You can think about the problem as like S chunks of a statistical problem. And if someone were to just give you the mathematical formula that came out of each one of these chunks, if that was the result that each of these machines produced, well, you would just take those math formulas and multiply them all together, and you would get the posterior distribution that you cared about, right? So the problem that we have is that the output of a Bayesian Monte Carlo analysis is a bunch of draws from these distributions, and so we have to figure out how to take those draws and combine them, right? There's two issues with this approach. One is I sort of, I kind of glossed over the fact that we have this prior distribution here, and we somehow need to get a working prior distribution for each of the worker level machines. It kind of looks, when you look at the problem this way, like you can take the prior and just write it to the 1 over s power, right? And then you can give a little piece of the prior to each of the workers. In some problems that works great, and in other problems it's a problem, right? Particularly in problems where the prior is there in order for you to do some sort of a regularization or model selection or something like that, then weakening the prior to that extent, if you take 1/1000th of the prior, then your kind of nicely regulated model and your Bayesian model selection might be wild and you'll end up with too many variables or something like that. But in other problems where the prior is representing your prior knowledge about something, then you can think about giving 1/1000th of your knowledge to each machine, and then the total amount of knowledge in the whole system would be conserved. I'm not going to talk about the prior beyond that. I want to acknowledge that it's potentially an issue. I'm not going to deal with the issue in the rest of this talk. What I will talk about is methods of forming or doing the recombination. My favorite, and this is from a paper that I wrote with like 6 other people in 2013, is to just simply average the draws, and I'll talk in a little bit about why that makes sense. I've had numerous conversations about this method with friends who are experts in sequential Monte Carlo, and they say, well, that just looks like a sequential Monte Carlo problem. So trying to do importance sampling and do things with particles is something that comes up a lot. Huang and Gelman thought about this way back in 2005. We're going to see pretty soon that that's something that's, yes, it does work, but it only works with, dimension up to 5 or so. And then the other idea that people have had is to think about Well, if what I really want to do is take these posteriors and multiply them together, well, why don't I just like come up with some sort of a model for the posterior distribution, right? And then I can multiply those models together. And one of the earliest ideas for how to do that came from Nieswanger and Xing, and I think that there's a middle author named Wang in this paper. And what they decided they wanted to do was to do kernel density estimates. So we'll take the posterior draws from each of the worker machines, we'll do a kernel density estimate, and then we'll multiply the kernel density estimates together. I mean, we sort of know that kernel density estimates break down after a while, right? Again, 5 or 6 dimensions, something like that. But there are examples in the literature of people fitting mixture models to much higher dimensional data. So we could think about, instead of doing kernel density estimates, maybe something like a mixture of normals. So we'll sort of explore that in a little bit. Now, among these methods, averaging is the only one that's never going to break, right? It might give you the wrong answer, but it's not going to collapse down to a single point like a particle might, and it's not going to like go off and fit some sort of a wild, weird model like the modeling won't. So whatever its flaws, averaging is kind of fast and easy and robust, and it does a good job in regular problems, whatever that means. To see why it might work, you might imagine how things would look if all of the sub-posterior distributions happen to be Gaussian. Okay, so imagine I've got machine 1, machine 2, and I'm denoting the sub-posterior for machine 1 as P1, and the sub-posterior for machine 2 is P2, right? So I've got a bunch of draws from P1 and a bunch of draws from P2, and really what I want is a bunch of draws from P1 times P2, right? Well, I mean, I know what P1 times P2 looks like, right? If they're both Gaussian, then if I think about this one as a prior and this one as a likelihood, that kind of looks like a Bayes rule, and I know what happens to the means and variances in Bayes rule. So what happens is that the P1 times P2 is going to look like a normal with a precision weighted average of the means, and the precision of the normal is going to be the sum of the precisions of the two factors in the product, right? Okay, so that's the distribution I want draws from. So let's suppose X is a draw from P1, so just one draw from my Monte Carlo sample from P1, and Y is a draw from my Monte Carlo sample from P2. Well, then if I take a precision weighted average of X and Y, obviously the mean is going to be this thing, and it's a 30-second exercise to show that the precision is the right precision, right? So what that says is that if I just do a precision weighted average of my draws from your draw 1 and your draw 1, I don't even have to do the ones in order. I can random shuffle them if there's some reason I want to do that. Then I'll get the right answer, right? In order to do this, we have to know the precisions, right? But of course, we've done a full MCMC, right? So I know what the precision is. All I have to do is take the variance, right, the sample variance of the MCMC draws and invert it, and I've got the weights that I need in order to do this weighted average. So that's kind of cool. So now let me show you some examples here. Here's my favorite example, right? This is a big data talk, and I've got 1,000 Bernoulli coin flips as my big data set. So the reason it's my favorite example is because we have a theorem here that says, hey, this is something that's going to work if all the sub-posteriors are Gaussian, right? Well, the way I'm going to engineer my 1,000 Bernoulli outcomes so that I only have one success, right? I've got one success and 999 failures, right? So nothing in sight here is Gaussian, right? And I'm going to take my 1,000 coin flips and I'm going to divide them up among 100 different worker machines, right? So each machine is only going to see 10 of my coin flips, right? So this is the sort of thing that you would expect is really going to break this example, right? Because not only is the full data posterior highly non-Gaussian, right? The worker level posteriors have even less data, so they're even more non-Gaussian, right? So they're even farther away from central limit theorems and things like that. Well, what's being shown here on the left-hand plot is I think the black line is the analysis that you get the actual beta distribution that gives you the right answer. And then what's being plotted here in the dashed blue line is what you get from the consensus Monte Carlo example, where you just combine things using the recipe that I gave you, using the weighted averages. And these don't line up perfectly, but they're awfully, awfully close. You have to do a QQ plot and sort of, kind of look way out in the tail in order to see where the discrepancies are. So the point I want to make from this slide is that, we have a guarantee in the Gaussian case, right? Things work. We know things are going to work if we do this kind of averaging thing with Gaussian posterior distributions, right? I've got a procedure that I can apply when things are non-Gaussian, right? And here's one example, right? When things are very heavily non-Gaussian and we apply the procedure that we know that works in the Gaussian case, and it works there too, right? So I like this procedure because there's at least some empirical evidence that it gives you some protection, right? There's a little kind of zone around the Gaussian distribution where if you're not too heavily far from it in some sense that I don't understand or know what it is, where things are going to work out okay, right? So it's different than me saying, oh, the posterior is normal, I'm going to compute the moments of the normal, and that's my posterior distribution, right? My posterior distribution here is a very non-normal thing that I got by averaging draws from non-normal sub-posterior distributions. Okay. You do have to be careful of the prior. So if you the uniform prior here is what I think what I used for the population, and so that's one prior success and one prior failure, obviously. If we take the uniform prior to the 1 over s power, literally, then you get the uniform prior for each worker machine, and that's not what we want, right? Because then we're adding 1,000 prior successes and 1,000 prior failures. My data only had one success in it, so 100 machines, so 100 prior successes, 100 prior failures. So by adding 100 prior successes to the system, we've really changed things a lot, right? In order to make this work, what you need to do is you need to take your one prior success and one prior failure and give each worker machine, if there's 100 machines, 1/100th of a prior success and 1/100th of a prior failure, and then things work out okay. So if you think about not taking the prior on the theta scale, on the probability scale, but on the logit scale, then the Jacobian works out so that the 1 over s thing gives you the right rule. So if you have a situation where your prior, where adding 100 times the prior that you intended to add would make a difference, then you need to be careful. If you're in a situation where you've got so much data that even if you had 100 times the prior information, it wouldn't make a difference, then you can afford to be sloppy, right? Okay. So that was not a big data problem or anything where it required scaling, but the type of problem that I might care about might be something like this. So I've got 24 million observations that have to do with people, being shown some sort of an ad and whether or not they click on it. And sometimes people might click on an ad, 0 or more times. Sometimes they can be multiple clicks. And so some of the analysts wanted to use a Poisson model to describe the ad clicks. So I have a relatively modest data set. My predictors include something called a quality score, which who knows what that is. There's some system that they already have at Google that is takes big data and it sort of spits out like how good an ad is, or maybe how good an ad might match a particular set of I don't know, user characteristics or something like that. But for a visitor to a page, there's a system that gives me this quality score. It's a continuous number. And then there's several different ad formats, right? I can choose to kind of put the text here or here. I can do all kinds of there's different ways of me showing the information in the ad. There might be 6 or 7 of these ad formats. And I've got coefficients that are going to vary by advertiser, right? So each advertiser has his own different type of ad that they show, and the ad formats might have a different effect on this advertiser than this advertiser, right? And so I've got data chopped up by advertiser. I've got 867 shards of data. I don't know how many advertisers I have, but I've got lots and lots of them, several tens of thousands of advertisers. And so each shard of data has something like 27,000 observations on it, right? So a shard of data is something where I could take 27,000 observations and run MCMC in R, right, using your favorite R package for doing Poisson regression, right? And my model is just, so the Poisson regression. So why is Poisson? There might be an exposure for the number if the ad was shown multiple times or something like that. And log lambda is beta j. So j is subscripting the advertiser times xij. That d should be a j, sorry. And just to keep things simple, I'm assuming the beta j's come from some normal distribution. So this is kind of a very, very standard Bayesian hierarchical model. The dimension of mu and sigma is, think about it as like 8 or 10 or something like that, right? So we can fit this model using consensus Monte Carlo, and you can kind of see the advantage, right? When you throw more and more and more machines at the problem, you can scale things up as big as you want, right? So it takes us about 20 minutes to fit this model, regardless of the number of shards that we throw at it. And if we try to run it on a single machine, then things sort of, at some point they hit a memory. You run out of memory point here, and you start paging. But on a single machine, you end up with very bad scaling behavior, with parallelism, you get, what you would hope for. We look at the posterior distribution of mu in this case that comes from consensus Monte Carlo. Do I have to do this? All right, okay. If we look at the posterior distribution of the mu parameters here, it kind of looks like this. So this is with 6 data shards, which is, it took a long time. One of the runs that we did that took a long time to run on a single machine. And along the diagonal, you can see the marginal distributions of each of the mu parameters. On the super diagonal, you can see the joint distribution of, add format 2 with the quality score, for example, right there, like in a pairs plot. The super diagonal, the plot is zoomed in on the action, right? On the subdiagonal, there's an actual axis where things are plotted on a common axis. So on the subdiagonal, because we have a lot of data, they're tiny little dots, right? The between coefficient variation makes everything hard to see. But we don't get exactly the same as we would have gotten on a single machine, but we do pretty close. And in particular, in plots like this one, where there's a correlation between the intercept and the add format 4 coefficient, we get that correlation about right? Which is nice. Okay. So we can do consensus Monte Carlo here to get posterior draws for the hyperparameters. We can compute the marginal distribution of the hyperparameters. What we really care about is the data level parameters, so the beta sub j's that are for the individual advertisers. Because what we want to do is we want to make advertiser-specific decisions, right? And if you think about this model, we're not going to be able to average across machines to get those coefficient level distributions right, because, well, there's no data for advertiser 2,374 on this machine. There's only one machine that has all the data for that advertiser. So there are no beta j's to average across the different machines. And so when we think about, the reason we did hierarchical modeling in the first place was to, pool information across advertisers. We're not getting that level of information pooling. What we can do, though, is we can do 2 passes, right? So we can do pass 1 to get the plot that I showed you that had the posterior distribution of mu, mu's and sigmas, right? So in pass 1, we can get this marginal distribution. And we can do, pass 2, right? Well, what is pass 2? Well, in pass 2, what we'll do is we'll take a draw of mu and sigma from the marginal distribution. And what that's represented by this big set of draws, right? When I say take a draw from the marginal distribution, we're just going to kind of do a multinomial draw from the set of draws that we did in the first pass. And then conditional on those draws, we'll take a draw of beta j, right? So that's something that we can do pretty easily. And the pass 2 is something that we can do completely in parallel, right? So we don't need, there's no communication necessary in order to do pass 2. You can do this with non-parametric models as well. So we tried this with BART, right? BART, for those of you that don't know, is Bayesian additive regression trees, right? BART is a sum of functions. Each of the functions happens to be a tree. And if you think about it, this sort of seems kind of weird, right? So in the previous examples, I was able to kind of average the parameters that came out of the MCMC, but there's no parameters in a tree. You can't average a tree, right? But we can average the predictive distributions, right? So the purpose of a non-parametric regression is someone to stick in an X and get a prediction out, right? So there's a predictive distribution that goes along with each X, and that's something that can be averaged. So this is an example that we ran. So this is Rob McCullough did this. Rob had a 30 core machine at his disposal, and so he took the biggest data set that he could run on a single core, and then he chopped it up into 30 shards. And what's being plotted here in the top row is the single machine algorithm versus the consensus Monte Carlo algorithm for the mean and the upper. The lower 2.5 percentile and the upper 97.5 percentile of the predictive distribution. Okay, so at those 3 points, the things kind of work out okay. In the interest of time, I think I'm maybe going to kind of not tell you what happens in the bottom row. Okay, so that's consensus Monte Carlo, and I just showed you some examples that would make you think, okay, this averaging is sort of not a bad thing to do. There's clearly going to be some examples where averaging is a dumb idea, right? If you know ahead of time that you're likely to have multi-modes or something like that, and you average, then multi-modes are going to get kind of, what's the saying? The donkey and the horse average together to make a mule or something like that. So that's not what you want to do. So if you're not going to average, what are you going to do? Well, Particles are an obvious idea, right? So I've got a whole bunch of draws from machine number 1, a whole bunch of draws from machine number 2, right? The draws from machine number 1 incorporate the prior as well as the likelihood component from machine number 1, right? So if I take all those draws and I ship them over to machine number 2 and I say, well, just evaluate the likelihood for all these draws and just resample with that likelihood, that's just sampling with importance resampling, right? There's other ways that you could do particles sequentially and things like that, but I think that's probably the cleanest way to do it. SMC people can please correct me if I'm wrong about that. And then the other thing that we could do is we could think about modeling the density of the draws, right? So I've got draws from machine number 1 and machine number 2. I can think about doing a kernel density estimate for machine 1 and kernel density estimate for machine 2 and multiplying those together, right? That was done by this Nieswenger paper and implemented by Miroshnikov and Conlon in an R package, so thankfully I didn't have to implement that. So this one and this one, I think we all have a strong prior that those are going to suffer from the curse of dimensionality. My thought was maybe we could try this modeling thing, but model a mixture of normals instead of a kernel density estimate, and see how that goes. The way the kernel density estimate, or sorry, the way the mixture of normals idea would work is I've got machine 1, and I'm going to decompose it as a mixture of normals. So I've got a bunch of mixing weights W's and a bunch of normal kernels F's. My F's have mean mu and variance sigma, mu1, sigma 1. Machine 2 is going to be a similar mixture, might have a different number of components, right? It's got mixing weights pi and mixing kernels g, so mu2 and sigma 2, right? If I multiply P1 times P2, if I believe this decomposition here, what I'm going to end up with is another mixture of normals that just looks like this, right? It's going to be kind of, think about it as I've got an array for P1 and an array for P2, and P1 times P2 is going to be the sum of things over a grid, right? And so what are the mixing weights and the mixing kernels in the grid? Well, so I'm going to call the mixing weights W tilde and the mean and the variance, I'm going to put tildes on things after they've been multiplied together, right? This is a homework problem for a grad student. So this is stuff you can all derive very easily yourself. We know what the precisions are going to look like. They just add together. We know the means are going to be precision weighted averages. The mixing weights, it involves not just the product of the two mixing weights, but the junk that's left over after you integrate over the kernels as well. You end up with this sort of product of precisions over sum of precisions and this thing over here which has some quadratic forms in it. The reason I'm showing you these forms is so that you can kind of get a sense of when would I have a big mixing weight. Well, I'm going to have a big mixing weight if I have components from either of the two mixtures that are big components, and so they have big mixing weights themselves. This thing is maximized when the precisions are identical, right? And these quadratic forms go to 0 when the means are identical, right? So if I have identical components, then I'm going to end up with a mixture component in the product that I am inclined to, that's going to have a big weight. All right. Well, okay, now that I have this product of mixtures, what can I do with it? Well, we got some robustness. One thing I guess I could do is I could just say, well, that's my answer, right? I've got a mixture decomposition that describes P1, a mixture decomposition that describes P2. If I multiply them together, okay, that's my approximation. But just like I had a procedure when I was doing averaging that worked for Gaussians, but would sometimes work even in a slightly broader setting, here I want to try and get some of that robustness out of this procedure as well, right? So what I want to do is I want to use this this product of mixtures in order to do local averaging. And what I want to do with the local averaging is to take a draw from the mixing weights, right? So I've got this big grid full of things that I add over for my mixture model. I want to take a draw from the different multinomial draw from the mixing weights in that grid, right? And if I end up in cell Km, right, then what I'll do is I'll take a random draw from all the different thetas that were produced by machine 1 that had been assigned to cluster K, right? So I would have to undo the mixture in order to figure out what I'm going to sample there. But of all the things that were assigned to cluster K, I'm going to pick one at random. And I'm going to take a random draw from the thetas from machine 2 that came from cluster M, right? And then I'll just average those two draws, right? And the weights I'll use would be the sigma 1 inverse sub K, so the sigma that came along from this cluster and the sigma that came along from that cluster, and I'll do kind of the averaging version of consensus Monte Carlo for those things. So even if my mixture approximation wasn't exact, I would still get some of the robustness that comes from just averaging in this thing. That's the hope anyway. Okay, so now let's see, we have 5 minutes or so. I'm going to show some examples. I'm going to do 3 examples here. In each of my examples, I have 8 workers, right? So I'm not going to do 1,000 workers or 100 workers like I did in the previous things because these are kind of harder examples here. The 3 scenarios I'm going to show you, I've got one where we've got multivariate normal posteriors. And so in that case, we know what the right answer is, right? The averaging the draws is the right answer there. I'm going to show you an example that's a one-dimensional example where distributions don't overlap. And then I'm going to show you something, I'm going to show you evidence that I don't run spell check on my talks before the inverse Wishart distribution. Those are my 3 examples. So in the multivariate normal example, I've got I'm going to do one with dimension 5, one with dimension 10, and one with dimension 20. And in each case, I'm just going to look at the first ordinate. So whatever x1 happens to be. And in this case, I'm showing you the results of the kind of, the consensus Monte Carlo where we average the draws. That gives us the right answer. SCMC is the sequential consensus Monte Carlo. This is the particle thing. The kernel consensus Monte Carlo, this is the Nieswanger kernel density estimate idea. And then the mixture consensus Monte Carlo, this is kind of the new Dirichlet process mixture thing I just described. And they all do great, right? So in 5 dimensions, things work great. In 10 dimensions, things start to break down, right? So here, the black line again is the right answer. The particles are sort of bouncing around the right answer, but what usually happens with particles in high dimensions is that all the weight falls on one particle, and and they get too concentrated in order to describe the full distribution, right? Interestingly enough, the kernel density estimate fails, right? In 10 dimensions, the kernel density estimate fails even for a multivariate normal, right? And so we end up with this kind of the center and the scale are both wrong for this estimate. The mixture distribution correctly identifies that there's only one normal in this mixture, and so it gets the right answer as well. And again, when we bump things up to 20 dimensions, things are similarly bad. Example number 2, I wanted to do a one-dimensional example where we had distributions that don't overlap, and so this is another one where I've got a bunch of successes and failures, like binomial data, but I put 90% of my successes on one machine and only 10% of my successes on the other machine, and similarly for the failures, right? So I've got perfectly symmetric beta distributions, but one is centered at 0.9, the other is centered at 0.1. Right, and this is the sort of thing that if you really had a one-dimensional problem and you were doing this problem by hand, you'd be an idiot to set it up this way, right? But if you had a 20 or 30 or 50-dimensional problem, this might be something that could happen in a subspace of your problem, and you wouldn't necessarily know that it was there, right? So this is the thing that's sort of a torture test. So here, what do we have? We have the exact method that we get if we just do the, kind of the proper beta distribution that we want. We have a dashed line here for the means, a dashed line here for the kernels. They both give basically the same answer, right? They sort of give the identical answer. We have this sort of bimodal density estimate. Really, this is 2 points, right? But the way kernel density estimates work, it's giving us like a hump here and a hump here. This is what happens with particles, right? So what you're going to do if you try to combine these things using particles is, whatever the smallest one was is going to go, all of these points are going to go get evaluated under this likelihood. Only the smallest one is going to be worth anything, right? And so all the weight's going to go here and all the weight's going to go there, and you're going to end up with that bimodal set of kind of particle density estimates. So resampling is going to break in a predictable way. What I think is interesting in this problem is what happens when we look at the mixture, the product of 2 kind of mixture draws. In that one, we end up with this kind of short, fat, lumpy distribution, right? Not very flattering words. So this is short, flat, and lumpy distribution. So that kind of seems weird. I would not have expected that to happen. So I was a little worried that maybe the mixture, my Dirichlet process program was getting the wrong answer, but when I look at the Dirichlet process approximation to the draws, it kind of looks right, okay? Dig down a little deeper, you could ask, well, how many components does the Dirichlet process think we have for these draws here? Well, it's detecting a little bit of non-normality, right? Because there's a slight left skew to this distribution, and so it thinks it needs either 2 or 3 or 4 components in order to affect that skew, right? Let's look at look at what happens when we just only look at the draws that had two components. Well, here's the draws of the means for the two components, and so there's some uncertainty about where to put the means. So both this distribution and this distribution are bimodal, but you'll notice that one of the distributions is significantly to the left, right? So it's trying to inflate this left tail by putting a normal over there on the left-hand side somewhere, and it's maybe not entirely sure exactly where to put the normal, right? It's also not sure how big a variance that other distribution should have. The tail inflator distribution, it's sort of oscillating between a couple of different choices for how big the variance should be, right? So when it comes time to do the mixture, the local weighted mixture approximation, let me look here. It's at any given point in time, it's trying to figure out which of these draws should I combine with which of these draws. And if you look at the mathematical formulas for the product of the two mixtures, the ones that get the very large mixing weights are going to be these guys over here on the edge, just like with particles. So the mixture decomposition is going to suffer basically the same sort of failure that the particles did. The last example I have is the only one where it's starting to get into a situation where it's a regular problem, but you might want to think about something other than averaging because of skewness, potentially. We've got a 3x3 Wishart distribution, which is, let's see, 1, 2, 3, 4, like 6 parameters, I think, in it. Let's see, so I've got a black line for the exact draws. I've got the average, the CMC averaging draws, or these guys right here, so there's a little bit of a difference. Nothing in this problem nails the right answer. The sequential Monte Carlo draws, at 6 dimensions, the particles again are kind of too spiky. The mixture draws wind up being very similar to the averaging draws, and the kernel density estimates again they get the shape of the distribution right, but there's a bias that shows up for some strange reason, right? When we bump the dimension up to 5 by 5, we see a sort of similar phenomenon. I'm showing you, just four elements from this 5 by 5 matrix. Interestingly enough, the kernel density draws and the Dirichlet process mixture draws, they both seem to be doing a slightly better job of getting the shape of the distribution right. The consensus Monte Carlo draws seem to be centered in the right place. So averaging is getting the average right, whereas the other draws are getting kind of other characteristics of the distribution. Right is the incorrect word to say here because it's not the right shape, but it's of all the shapes that are on the slide, it's the one that's closest. All right? Okay. There's other methods that I haven't discussed here. I don't want to give the sense that this talk is an overview of everything people have done in the divide and recombine or consensus Monte Carlo world, because there's other stuff out there. I wanted to focus on these particular methods because when I talk to people about this method, these are the ones that people bring up the most. But people are doing other interesting things in this space. So things that deserve special mention are Andrew Gellman has a method for doing expectation propagation, which is it's a method that handles the prior distribution more gracefully than I do. But it's very similar in other respects to the Dirichlet process modeling. I'm out of time, so I'll just kind of mention that there's a couple other things out there. And I want to mention specifically the poster that's outside by Callum Viner. I hope I didn't butcher his name too much, which I think does a pretty good job of taking these ideas and coming up with a reason that you can sort of scale them down to low-dimensional summaries where the cursor dimensionality might not bite quite so hard. So with that, I think I'll just say thank you very much.
Any questions for Steve?
In the mixture approach, what happens if you replace the normals by a polynomial tail distribution like the student's t? Or
You mean if I use mixtures of students' t's as opposed to mixtures of normals? I don't know. I mean, I chose normals because the theorem that we have that says things work with normals, and so normals are kind of an obvious mixture component to use. I haven't tried it with t's.
And Sylvia?
Have you got examples of more complex hierarchical models where, this second pass, involved can that be, and what does that create any difficulties for the structure?
So I don't necessarily know how to do hierarchical models with, say, crossed random effects, for example. my strategy, if I wanted to do a more complex hierarchical model, is to make sure it follows some sort of a nesting. And so even if I didn't think that there were going to be interactions between random effects present, I would put them into my model so that I could get that multiply nested thing. If you have a deeply nested hierarchical model, you can repeat the phase 1, phase 2 trick that I did here and just kind of repeatedly attack the data, and which I think is a perfectly fine thing to do. So an extra 30 minutes fitting your model for data sets of this size is not a big deal. And so if it takes 3 30-minute chunks instead of 2 30-minute chunks, I don't think that's a problem. But I do think it is limited in terms of some of the models that you can fit. If you wanted to have theta 1 for the ad and theta 2 for the user or something like that, and they didn't have an interaction between them for whatever reason, then it's not clear to me how the algorithm would work.
Okay, so can we thank the speaker again?